So, I wanted to show you also blades of different stages in order to show you the huge difference existing between H or H over C, because we like non-dimensional parameters, so H over C is non-dimensional, between a first stage, you need to show it like this, the flow is coming from there to this direction, and the last stage, where you have, that is something like this, so at this position. So you see the huge difference existing between two stages. Here we have H over C, which is most probably in the region of 3 or something like that. Here H over C is more in the region of 1. And you can even have something much smaller like this. So you see this blade with also the leading edge that has been degraded, which is with a H over C only something like 0.5, much, much smaller. So you see the difference. When you have a problem over, let's say, 0.5 centimeters, 5 millimeter here, this is half of the blade. Here, 5 millimeters, this is 10% or 5% of the blade. So you understand that the situation is not at all the same if you are in the final stages or in the first stages for the same degradation of, let's say, the leading edge or, let's say, a part of the blade. This is very, very clear. But let's say if you avoid all these problems, if you take a lot of, let's say, margins, technical solutions with variable inlet guide vanes, wide chord blades, if you have leading edges of blade that have been reinforced using laser shot peening, for example, we could ask the question, as we said at the end of the last lesson, why do we need such a distance between the surge line and the steady state line? The surge line is here, the steady state line is here. Why do we need such a distance between them? Because it's a loss of performance. You could rise the surge line, the steady state line, so it's going nearby the surge line. So the question is, why is not the surge margin equal to, let's say, 1%? Why is it not the case? Why are they going to 10%, 15%, 20%, 25%? Why is it so large? And this is, of course, related to a certain loss of performance. It's very clear. And what is the reason? The reason is certainly that we have, let's say, forgotten or that we have not considered until now some phenomena that will take place. In fact, what will happen, you will have the steady state line can, for different reasons, go up. So the steady state line can have a movement towards the upper direction, and the surge line can have, on the contrary, movements going to the lower direction. What are these reasons leading to a movement downward of the surge line and a movement upward of the steady state line? There can be different reasons. We have seen one here downwards on downstairs on the fan disc or fan of the F100 tolerances. So with time, the blades are moving. The blades are degraded. So the leading edge is not anymore at the place you wanted to have it. The leading edge has been deformed. So these are certainly very good reasons leading to the fact that the surge line will go down, will go down, will go down. Okay? But this is explaining maybe in the 25% you have here, maybe it can explain 1% or something like that. 1% due to the tolerance of the movement of the blade, 1% due to the shape of the blade that is changed due to impact with stones or birds or things like that. So it cannot explain this variation. But there are a lot of other reasons. Another reason you can have also, this is the fact that you are extracting power out of the engine. This is what is called the pot. We have discussed that in the installed performance. I said to you we are taking electrical power for the aircraft, for example. This is power that we extract out of the engine, out of the shafts of the engine. This is called the pot, the power of take. So we take power out of the engine. And what is the problem? Very often the pot, this is something that is about constant. Because you need to have the lighting on board, for example. You need to have the electricity for the seats, for looking at the videos. You need some electricity also maybe to warm up some dishes and things like that. You need to have the electricity for the avionic bay, so for the radar, for a lot of different flight systems. And this pot is, let's say, roughly constant in flight. But the problem is that the power on the shaft, where you extract this pot, from which you extract this pot, is decreasing with the altitude. So when you are going to altitude, you have a huge difference in power on the shaft, but you take the same amount of kilowatt to drive the accessories. So the percentage of that compared to this is increasing. And at a certain moment, you can be forced to increase the position of the steady state line due to that, because you don't have enough power on the shaft to extract this pot, and so you need at high altitude, at higher and higher altitude, the danger to being forced to do that is really increasing. So you see, bit strange to discuss that, because it's looking like something that could not be, let's say, guessed before. Also something that you can have, this is the fact that the VSVs are also called sometimes the RCVVs, the rear compressor variable vanes. So this geometry, this variable geometry that you have in the compressor is less precise, is a bit degraded, not working in the same way on all blades with time. These are, let's say, degradation at the level of the maintenance, at the level of the accuracy of some elements. But all this together, you can have also Reynolds number effect at very high altitude that makes that the search line will go down. But all this together, maybe you will reach something like 5% altogether. Altogether, something like maybe 5%. So where are the 10, 15, 20 other percents that are leading to this search margin? In fact, there are two main problems that are leading to the search margin. So two main issues, two main reasons leading to the search margin. The first one is something that we have discussed already, but not so much into details. This is distortion. The fact that on the blade, you are arriving on the compressor, first stage, a second stage, a third stage, that you are arriving on the compressor with a flow that is not uniform. So not the same speed, not the same angle, not the same mass flow rate, not the same I don't know what, not the same pressure, temperature on each blade, on each square centimeters of this front section you have. And the second reason are what we call the transients. The transients. So that means the variation of the rating, the variation of the flow, the fact that you change the operating point of the engine. And globally speaking, we can say that maybe 10% of the search margin is coming from there and 10% from here. So you see these two alone are larger than the sum of everything that I've indicated before, related to wear, related to maintenance that is not done adequately, that should be done, that is not be done, the pot and things like that. So I would like to explain these two ones, the distortion and the transients. So I repeat, what do I call distortion? What do I call distortion? You take the engine phase, so the engine phase, and this is the fact that you will have pockets, you will have pockets that can have different shapes, maybe a shape like this also, where you will have in these pockets a parameter of the flow that is not the same. It can be the orientation, so not axial, but with a certain angle, let's say, in this direction, or the pressure, the static pressure, the total pressure, the speed, that with a static pressure difference can lead to a total pressure, the mass flow rate, that can be different, the temperature, the total temperature. There can be a lot of reasons. And that makes that when the blade is turning, the blade is turning and the blade is seeing this flow, and then 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 this flow, this flow, this flow, this flow, this flow, this flow. You see that over 360 degrees, the blade is seeing regions with different parameters, orientation of the flow, and mainly we know a problem with the axial velocity. Due to the mass flow rate, due to the orientation of the flow, they can be certainly one of these two reasons or a combination of these two reasons. And you can see the problem as, so the blade is having a certain chord, and the blade is turning here. And the blade is seeing this perturbation, the blade is rotating, let's say, clockwise. The blade is seeing this perturbation during, let's say, 10 degrees. And during these 10 degrees, the perturbation is entering. And if, at this point, the perturbation is only there, you see that the blade will not react wrongly, because you have still this part of the blade that is sane. But if, when you arrive here, the perturbation is here, you have contaminated the whole blade, and then the whole blade will react non-adequately, and that can lead certainly to a surge. This is a very complex problem, very complex problem, the problem of distortion, but we can understand that the variation of the flow conditions is leading to a problem. Everybody with what you know today can certainly understand that this is a dangerous situation. Now, making the link with surge, I can understand that there is a problem, but is it really dangerous? What is the effect on the surge line? So I say you, the surge line can move seriously down, going here. So this is the surge line without distortion, and this is the surge line with distortion.